Look up at the night sky. For millennia, we saw only points of light, weaving stories of gods and heroes. Now we see something else. We see our own creations looking back down at us. These are satellites, our silent guardians orbiting high above. They are our extended senses, allowing us to perceive our planet in ways our ancestors could only dream of. We use them to predict the weather, to navigate our cars, and to connect with one another across vast oceans. But what if these eyes in the sky could do more? What if they could help us understand the very air we breathe and its hidden connection to our well-being, even to the most complex diseases that afflict us? It is a profound thought. The same technology that explores distant galaxies might hold clues to the health of a single human being. The universe is a story of connections. The iron in your blood was forged in the heart of a dying star billions of years ago. The water you drink may have arrived on comets that traveled from the outer reaches of our solar system. Everything is linked. In this grand cosmic narrative, it should not be so surprising that our health is intimately connected to our environment. The planet is not just a stage on which we live our lives. It is an active participant. Its atmosphere, its chemistry, its cycles of life and decay are all part of us. By turning our instruments towards Earth, we are, in a very real sense, turning them upon ourselves, seeking to understand the intricate dance between our biology and the chemistry of our world. From this vantage point, high above the clouds, our planet reveals its secrets. We can see the swirling patterns of hurricanes, the slow crawl of deserts, and the vibrant green of rainforests. But we can also see the invisible. Satellites equipped with specialized sensors can detect chemical signatures in the atmosphere, many of which are completely invisible to the human eye. They can measure gases released by factories, forests, and traffic-clogged cities. This is where our journey begins. We are going to explore how this cosmic perspective, this ability to see the unseen from hundreds of kilometers up, is opening a new frontier in public health. We are using the tools of astrophysics and planetary science to investigate a terrestrial mystery, the potential environmental triggers for a devastating brain cancer. Imagine a detective story on a planetary scale. The crime scene is our own atmosphere. The victim is human health, and the clues are faint chemical whispers, captured by robotic detectives circling the globe. This isn't science fiction. This is the remarkable reality of 21st century science. We are embarking on an investigation that connects the vast emptiness of space with the microscopic world of our own cells. It's a quest to understand if the byproducts of our industrialized lives, floating unseen above our heads, could be influencing the risk of developing diseases like glioblastoma. Let us begin our exploration, not in a laboratory or a hospital, but in orbit, aboard our sentinels in the sky. Deep inside the most complex object we know of in the universe, the human brain, a formidable enemy can arise. It is called glioblastoma. This is not just any cancer. It is the most common and aggressive type of primary brain tumor in adults. It forms from star-shaped cells called astrocytes, which are supposed to support and protect our neurons, the very cells responsible for our thoughts, memories, and emotions. But in glioblastoma, these supportive cells turn against us. They begin to divide uncontrollably, forming a tumor that grows rapidly, weaving its way through the delicate fabric of the brain. Its aggressive nature makes it incredibly difficult to treat, a challenge that has perplexed doctors and scientists for decades. The causes of glioblastoma remain largely a mystery. For most people who develop it, there is no clear reason why. We know that certain rare genetic syndromes can increase the risk, and exposure to very high doses of ionizing radiation is a known, though uncommon factor. But these account for only a tiny fraction of cases. This leaves a vast, unanswered question. What else is at play? Scientists have long suspected that environmental factors, the chemicals we are exposed to in our daily lives, might be part of the puzzle. The brain is protected by a special barrier, but it is not impenetrable. Could something in the air we breathe be a contributing factor, a piece of this complex and tragic puzzle? This is where the story shifts from the purely biological to the environmental. Think about your daily life. You breathe in the air in your home, your workplace, and your city. This air is a complex cocktail of gases. The vast majority is harmless nitrogen and life-giving oxygen. But mixed in are trace amounts of other chemicals, some natural, some man-made. These include pollutants from vehicle exhaust, industrial emissions, and even natural processes. The central question for researchers is whether long-term, low-level exposure to certain of these airborne chemicals could, over many years, increase the risk of the cellular mutations that lead to cancers like glioblastoma. It is a vital and urgent line of inquiry. Understanding these potential environmental risks is not about creating fear. It is about empowerment. If we can identify specific pollutants that are linked to a higher risk, we can take action. We can create policies to reduce their presence in our atmosphere. We can design cities that are healthier. We can provide people with information to help them make choices that might lower their exposure. Finding these links is the first, crucial step. It is a scientific detective story where the clues are not fingerprints or fibers, but molecules floating in the air. And to find them, we need a witness with a very, very wide view. We need to go to space. To monitor a whole planet, you need a fleet of observers. That is precisely what the European Space Agency has given us with its Copernicus program. Think of it as Earth's own dedicated team of robotic checkup artists. Among the most important members of this team are the Sentinel satellites. Each one is a marvel of engineering, designed for a specific task, working in concert to give us the most complete picture of our world's health ever assembled. They are our sentinels, standing guard from orbit, and they are constantly collecting data, beaming it back down to us on the ground. 3 of these sentinels are particularly interesting for our story: Sentinel-2, Sentinel-3, and Sentinel-5P. Let's start with Sentinel-2. Imagine you are flying over the land in a very high-altitude plane with a superpower camera. That is Sentinel-2. It takes high-resolution color pictures of the Earth's land surfaces. It can see fields, forests, rivers, and cities in incredible detail. Its main job is to monitor things like crop health, deforestation, and urban sprawl. For our investigation, it provides the context. It shows us where the cities are, where the major roads are, and where the industrial parks are located. It draws the map upon which we will overlay our chemical clues, giving us a physical reference for any pollution hotspots we might find. It tells us where things are happening. Next up is Sentinel-3. This one is a multitasking workhorse. It has a broader view than Sentinel-2 and measures the temperature, color, and height of the Earth's surface, both land and sea. Think of it as the planet's thermometer and health monitor. It tracks sea level rise, measures the heat radiating from cities, the urban heat island effect, and monitors the health of ocean ecosystems by looking at their color. While not directly measuring air pollution, its data on land surface temperature is valuable. Many chemical reactions in the atmosphere are influenced by temperature, so Sentinel-3 adds another crucial layer of information to our growing understanding of the environment below. Finally, we come to the star of our show. Sentinel-5P. The P stands for precursor, as it is paving the way for future instruments. This satellite is not about taking pretty pictures. It is a specialized atmospheric chemist. Its instrument, called Tropomi, is designed to do one thing exceptionally well: measure the composition of the air. It stares down at the atmosphere and detects the unique spectral fingerprints of various trace gases. It can measure nitrogen dioxide from traffic, ozone, sulfur dioxide from volcanoes and industry, and, crucially for our story, formaldehyde. It cannot see every chemical, but the ones it does see provide powerful clues about the chemical processes happening in the air we breathe, right down to the city level. So, our space sentinel, Sentinel-5P, can detect formaldehyde. But what does that have to do with brain cancer risk? The connection is a piece of chemical detective work. Formaldehyde itself is a known carcinogen, but scientists are often interested in it as an indicator, a proxy, for other things. In this case, it is a clue to the presence of another, more elusive chemical, ethylene. Ethylene is a simple organic molecule, a gas that is widely used in the chemical industry, particularly in the production of plastics. It is also released from the burning of fossil fuels, meaning it is present in vehicle exhaust. Some studies have suggested a potential link between occupational exposure to ethylene and certain cancers. Now here is the challenge. Our satellites cannot directly see ethylene in the lower atmosphere. Its chemical signature is just too difficult to pick up from space. But chemistry gives us a way around this. When ethylene is released into the atmosphere, it does not just stay as ethylene. It reacts with sunlight and other chemicals in the air. One of the main byproducts of this reaction is formaldehyde. So, where there is a lot of ethylene being broken down, we expect to find a lot of formaldehyde. The formaldehyde becomes a chemical breadcrumb, a signpost pointing back to its source. It is an indirect but scientifically solid method of tracking our target. The process then looks like this. First, the Sentinel-5P satellite orbits the Earth, its TROPOME instrument scanning the atmosphere below. It measures the concentration of formaldehyde gas, creating a global map of its distribution. These maps are not just single snapshots. They are built up over days and weeks, revealing persistent patterns. We can see hotspots of formaldehyde hovering over major industrial regions and sprawling urban centers. But this raw data is just the beginning. To get from a map of formaldehyde to an estimate of ethylene, scientists must use another powerful tool: atmospheric chemical models. These are complex computer simulations that mimic the physics and chemistry of the atmosphere. Scientists feed the satellite's formaldehyde measurements into these models. They also add in other data such as weather patterns, temperature from satellites like Sentinel-3, and information about the location of roads and factories from satellites like Sentinel-2. The model then works backwards, calculating how much ethylene must have been present in the first place to produce the amount of formaldehyde that the satellite detected. It is like seeing a puddle on the ground and using your knowledge of weather to calculate how much it must have rained. The result is a new map, an estimated map of ethylene pollution, which we can then compare with health data to look for correlations. Let's bring this down from the stratosphere and into our daily lives. Imagine a sprawling city like London or Manchester. From the ground, it is a mosaic of neighborhoods, parks, and busy streets. From space, our satellites see it as a complex pattern of chemical signatures. Using the methods we have discussed, scientists can create a pollution map of the city. This map will not be uniform. It will show distinct hotspots, areas where the estimated levels of pollutants like ethylene are consistently higher than in other parts of the city. These hotspots often appear exactly where you might expect them. For example, a major motorway, like the M25 circling London, will likely show up as a ribbon of higher pollution on our ethylene map. Every day, tens of thousands of cars and lorries travel along this road, their exhausts pumping out a cocktail of chemicals, including the precursors to ethylene. Over time, this creates a persistent corridor of elevated pollution that can affect the surrounding neighborhoods. Similarly, an industrial estate on the outskirts of a city, particularly one with chemical or plastics manufacturing, might appear as a concentrated red blotch on the map. These are areas where the chemical ingredients for pollution are constantly being fed into the local atmosphere. Now, let's consider a more subtle example. A large hospital is often a hub of activity. It has significant road traffic from staff, patients, and visitors arriving by car. It might also have its own power generation facilities or laboratories that produce emissions. Using satellite data, we could analyze the air quality specifically around these major medical centers. We could see if the combination of heavy traffic and institutional operations creates a local pollution hotspot. This is not to say that hospitals are uniquely dangerous, but that they are complex environments within the urban landscape that warrant study. The satellites give us the power to ask these specific questions on a grand scale. The real power of this approach is its ability to see the big picture and compare different areas. We can compare a quiet, leafy suburb with a dense urban center built around a major transport interchange. We can see how pollution levels change between a large public park and an area downwind from a factory. These are not just abstract data points. They represent the different environmental exposures experienced by the people living, working, and going to school in those areas. By identifying these persistent hotspots, we can begin to ask the critical health question: do people living in these high pollution zones for many years show a higher incidence of diseases like glioblastoma? The satellite data gives us the starting point for that investigation. Our sentinels in space are magnificent tools, but they are not all-seeing. it is crucial to understand their limitations. A satellite like Sentinel-5P is looking down through the entire column of the atmosphere, hundreds of kilometers deep. It gives us an average concentration of a gas over a fairly large area. The smallest patch of ground it can resolve is still several kilometers across, roughly the size of a small town or a large airport. This means it cannot tell you the difference in air quality between one side of a street and the other, or between your front garden and your back garden. For that kind of detail, its vision is simply too coarse. This is where ground-based tools come into play, providing what scientists call ground truth. Imagine a hospital wanting to know the precise air quality in its operating theaters, or on the ward where its most vulnerable patients are recovering. A satellite image showing a general orange haze over the entire hospital campus is not useful enough. For this, they need highly sensitive local gas sensors. These devices can be placed directly in a room and provide continuous, real-time measurements of specific chemicals with incredible precision. They can detect tiny fluctuations that a satellite would completely miss, offering a level of detail essential for ensuring patient and staff safety within a building. To bridge the gap between the satellite's broad view and the sensor's pinpoint measurement, we have another exciting technology: drones. An unmanned aerial vehicle or drone can be equipped with lightweight, miniaturized air quality sensors. It can then be flown at low altitudes along a specific route, for instance, around the perimeter of a hospital or along a busy road next to a school. This allows scientists to create a high-resolution, three-dimensional map of pollution in a very specific area. The drone can measure how pollution levels change with height and distance from a source, providing a richness of detail that is impossible from either space or a fixed ground station. The ultimate strategy is not to choose one tool over the other, but to combine their strengths. The satellite provides the wide area context, identifying large-scale hotspots across an entire region over many years. This is something ground sensors could never do. The drone can then be deployed to investigate those hotspots in greater detail, mapping the pollution street by street. Finally, fixed ground sensors can provide the continuous, high-precision data needed for specific locations, like a hospital ward or a classroom. By weaving together data from space, the air, and the ground, we can build the most complete and accurate picture of the air we breathe. To make pollution data useful for everyone, not just for scientists, we need a simple way to communicate risk. Think of a traffic light system: green, orange, and red. It is a universal language for safety, and we can apply the same logic to air quality. By analyzing the estimated ethylene concentrations from our satellite and model data, we can categorize different areas of a city into these risk bands. This helps public health officials, city planners, and residents understand the environmental quality of their neighborhoods at a glance, turning complex chemical data into actionable information. Let's define what these colors might mean. A green zone would be an area where the long-term average concentration of a pollutant, like ethylene, is very low, well below any established health guidelines. These are typically areas with plenty of green space, like large parks or leafy suburbs far from major industrial sites or motorways. Living in a green zone would suggest a lower environmental risk associated with this specific pollutant. It represents the ideal that city planners should strive for, creating healthier spaces for people to live and work. These areas serve as a crucial baseline for comparison against more polluted parts of the city. An orange zone would indicate a moderate level of pollution. These are areas where the estimated concentrations are noticeably elevated above the green baseline, though perhaps still within older regulatory limits. You might find these zones in denser residential areas with moderate traffic, or downwind from light industrial activity. An orange designation is a caution sign. It suggests that while the risk is not acute, long-term exposure could be a concern, and that the area warrants monitoring. For city officials, an orange zone is an early warning, a signal that policies to improve air quality, like promoting public transport or creating low-emission zones, are needed to prevent it from becoming a red zone. Finally, a red zone represents a high level of pollution. These are the hotspots we identified earlier, where long-term average concentrations consistently exceed health and safety guidelines. These are often found along the busiest transport arteries or clustered around heavy industrial facilities. A red designation is a clear warning that the environment in this area is unhealthy. For public health research, these red zones are of primary interest. They are the locations where we would most urgently want to compare pollution data with health records to see if there is a statistical correlation with diseases like glioblastoma. For residents, it is vital information that can empower community action and demand for cleaner air. The true breakthrough in this field will come not from a single source of data, but from weaving together multiple, complex data sets into a single, coherent tapestry. Imagine combining the power of our cosmic gaze with the detailed personal information stored in our health records. This is the frontier of epidemiology and environmental science. By merging anonymized health data from large populations with the environmental data captured by our satellites over many years, we can begin to search for the subtlest of patterns that connect our environment to our health outcomes on a massive scale. The first thread in our tapestry is the satellite pollution data. As we have seen, this gives us a map of estimated ethylene concentrations, categorized into our green, orange, and red zones for an entire city or region. But a single map is just a snapshot. The real power comes from having these maps for every month, every year, stretching back a decade or more. This creates a historical archive of pollution, showing how hotspots have evolved, shifted, or intensified over time. This temporal dimension is absolutely critical, because cancers like glioblastoma can take many, many years to develop. The exposure that matters may have happened long in the past. The second thread is anonymized health data. Hospitals and national health services maintain vast databases of patient records. For our purposes, we would be interested in data that has been stripped of all personal identifiers, like names and specific addresses, to protect privacy. What would remain is the crucial information, the type of diagnosis, for example, glioblastoma, the date of diagnosis, and the general location of the patient's residence, perhaps narrowed down to a postal code or census district. This creates a health map, showing where and when cases of the disease have occurred across the city over the same time period as our pollution maps. The final step is to weave these threads together using powerful statistical analysis. We overlay the historical health map onto the historical pollution map. The computer can then search for correlations. Does a census district that has been in a red pollution zone for 20 years show a statistically significant higher rate of glioblastoma diagnoses than a district that has consistently been green? Do we see a lag time, where a spike in pollution in one decade is followed by a rise in cancer cases a decade later? This is big data science in action, searching for faint signals within a sea of noise. It cannot prove that pollution caused the cancer in any single individual, but it can reveal powerful population-level risk factors. So where does this leave us today, on the 11th of June, 2025? Let's summarize the current state of play. We have incredible tools at our disposal. The Sentinel satellites are in orbit right now, providing a continuous stream of invaluable data about the chemistry of our atmosphere on a global scale. This is not science fiction, it is a present-day reality. We can use this data to create large-scale maps of pollutants and identify regional hotspots. This is immensely useful for understanding broad environmental patterns, for informing climate models, and for guiding public policy on a citywide or national level. It gives us the big picture, the context for everything else. However, we must be clear about the limitations. Today, you cannot use a satellite image to diagnose an individual's risk for brain cancer. The resolution is too coarse, the chemistry too indirect. If a hospital needs to ensure the air in its surgical suites is pristine, it will not be looking at a satellite map. It will be using highly specialized, on-site ground sensors that provide precise real-time measurements. For detailed, street-level pollution mapping, a sensor-equipped drone is a far better tool than a satellite orbiting 800 kilometers overhead. For now, the tools for immediate local health and safety remain firmly on the ground. The future, however, is about integration. The vision is to build a system where these different scales of measurement work together seamlessly. Imagine a future where the satellite detects a new persistent pollution hotspot emerging over a city. This could automatically trigger an alert, and a fleet of autonomous drones could be dispatched to map the area in high-resolution detail. The findings could then be fed into public health dashboards in real time. By connecting this rich, multi-layered environmental data with long-term anonymized health records, we might one day be able to generate predictive risk maps for a whole range of environmental diseases. The journey from a faint chemical signal in space to a meaningful insight about human health is long and complex, but it is a journey we are on. The connection between the cosmos and ourselves is not just poetic, it is becoming a practical tool for safeguarding our future. By continuing to look up at our sentinels in the sky, we learn more about the delicate and intricate workings of our home planet. And in doing so, we learn more about ourselves, opening new pathways to a healthier world for everyone. The universe is in us, and by studying our world from afar, we may find the keys to protecting the universe within.